Okay, just to make sure we're on the same page, I'm going to give a super quick introduction to the position, velocity, and acceleration standard, just so you know what I expect you to know. Okay, so this is called PVA, position, velocity, and acceleration. So the first thing is the definition of velocity, average velocity, and this is all in one dimension, 1D. Average velocity is the change in position over change in time. Remember, that delta means change in. So this is really x2 minus x1 over t2 minus t1. Be careful. I see people put in things down here for delta t that is not delta t. So be careful about that. Okay? Okay, that's the first definition of average velocity. We have another definition of average velocity. If the acceleration is constant and the velocity is changing, then I can say this. v1 plus v2 over 2. You can actually just take the starting velocity, the final velocity, add them together, divide by 2, and get the average, and that's the average velocity. So this can be equal to this, and that's going to be useful. Finally, we have this. The acceleration is the change in velocity over change in time. v2 minus v1 over t2 minus t1. And again, I'm just using that delta to say change in. This is technically the average velocity, but we never deal with, the average acceleration. We don't really deal with changing acceleration too much, not in kinematics form. So you don't have to worry about that. So we'll just call that acceleration. Now, the next big thing is that I can use all these three together, and I've already derived it once, but I won't do it again, and I get this equation, x2 equals x1 plus v1 delta t plus 1/2 a delta t squared. So that's just using these three things together, I can get that equation. This is a relationship between the final position, the initial position, the initial velocity, the acceleration, and the time. There is another kinematic equation, but I don't think I want to worry about that one yet. If you want to memorize it, that's fine, but if you use it, you want to at least show where it comes from. Okay. Also, from this definition of average velocity, I get what's called the position update formula. And we use that in numerical calculations. It says the final, I can't really read that. Write a little bigger. x2 equals x1 plus v average delta t. So if I know the velocity and I know the time and I know where it started, I can find the new position. That's the position update formula. And likewise, we get the same thing, similar thing for the acceleration. I get the velocity update formula. The acceleration times the time interval, plus the old velocity gives me the new velocity. That's it. Okay. Now there's one other thing I want to show, and that's this connection between position, velocity, and even acceleration graphs. And we touched on this, but it's something that we're going to use more often, so it's important to know what it would look like. Let me start with the graph of acceleration as a function of time for constant acceleration. So this is an object that just has an acceleration that's not changing. Really, we can deal with this, and we can deal with piecewise constant. So it can be constant and then constant some other value. If I want to consider what this does to the velocity, since velocity is the change, since acceleration is change in, since velocity, v2 is v1 plus a delta t. This a delta t is important because if I have this is delta t and this is a, then a delta t is that area. So the area under a delta t gives me the change in velocity. It doesn't give me the velocity because I need to know what it started with. Okay, but you can see as I move along, the velocity is going to be increasing. So that would mean the velocity versus time graph would look something like this. I'm going to put it down here. So the velocity time graph, as this thing increases, the velocity increases. So as I move along that way. Notice I put the velocity starting as some negative value because we don't know anything from just that graph. But we do know this. The slope of this is going to be the rise over the run, so that's going to be equal to change in v over change in t. Oh, that's the acceleration. Positive slope, positive acceleration. Finally, we have the same thing we can say over here, the area under this curve, since x2 equals x1 plus v average delta t. V average in this case would be also the area. It's a slope, but that's like finding the area of a triangle because we're doing v1 plus v2. But the area under this curve is also the position traveled. So in this case, I get something like this. I get a parabola for the position versus time. Now, the important thing to note here, oh, this is bad, because I have a negative velocity. So it would actually look like the velocity is increasing, but starts off negative, and be like this. Yeah. So, yeah. So right here, the velocity is 0. The slope of this graph is delta x over delta t equals the velocity. So at the slope at any point here, the slope's negative. Here the slope's 0. Here the slope's positive. And so you can see going from negative velocity to 0 velocity to positive velocity. And there you go. I know that's super quick, but it's just a video. That's the position, velocity, and acceleration standard.